So without further ado, I'm just going to hand it over to Santosh and Craig from DRS Daylight Solutions. Gentlemen, please take it away.
Oh, thank you very much. This is Craig McGee speaking, and today I'd like to share with you our slides for real-time protein analytics using a laser-based quantum cascade laser IR system for real-time, non-destructive biophysical characterization of your biologics. And so the talk today will be broken up between myself and my colleague Santosh. And our basic agenda is we'd like to talk about some of the current demands in biopharma, additionally some of the current challenges with biophysical characterization, and then talk about the QCL mid-IR advantage for these types of measurements. So pharma continues to demand instrumentation that increases throughput and provides the most reliable data. And there are many techniques that are commonly used by scientists for quantitation and characterization, but all these techniques have unique challenges. Therefore, it's important to have a PAT solution that will be compatible with existing system interfaces and support the development of methods that can easily be transferred downstream. So it turns out in vibrational spectroscopy that UV-vis spectrophotometers are the most prevalent workhorse instruments for taking measurements for sample concentrations. However, ultraviolet lacks the sensitivity needed to measure broad ranges of concentrations and typically requires dilutions at higher sample concentrations. Additionally, UV lacks the spectral selectivity for determining specific chemical information such as secondary structure, level of glycosylation, bioconjugation reaction monitoring, and intermolecular interactions. Near-infrared instruments, while suitable for some applications, are met with challenges in the characterization of biomolecules, as the near-infrared chemical vibrational signatures, or secondary overtones, are typically quite broad and lack the selectivity or fingerprint to characterize the chemistries involved. So what about infrared then? Well, typically infrared, or more specifically mid-IR, is referred to as the fingerprint region of the spectrum for characterizing the vibrational states of biomolecules and small molecule conjugates. Mid-IR is useful for probing amino acids, nucleic acids, proteins and peptides, saccharides, and even reaction monitoring of peptide synthesis and bioconjugation reactions in both aqueous and also organic solvents. So it turns out that mid-IR has significant advantage for characterizing biologics due to the high selectivity of the molecular fingerprint for direct quantitation. Both large molecules and small molecules have large cross-sectional vibrational areas, which allow to high sensitivity and the ability to probe secondary structure. The simple application of Beer-Lambert principles through transmission studies allow for direct quantitation without the worry of autofluorescence backgrounds. And also, since you're doing primary detection of your molecule, you can conduct your analyses without the worry of adding labels, tags, or dyes to your mixture. So this begs the question, well, why isn't mid-IR more commonly used for liquid analysis? And it turns out that water is the answer. Traditionally, conducting analysis of biomolecules in the mid-IR has been met with significant difficulty due to the very strong absorption bands of water, making it nearly impossible to pass light through the sample. And specifically, measuring vibrational states of the peptide or the amide bond has been a challenge for traditional spectrometers and often requires a sophisticated water correction model in order to be quantitative. And in cases where data may be collected in these regions, the dynamic range is often quite limited and the data collection is quite convoluted. So, traditional workhorse technologies like FTIR, ATR, and Raman have been the significant players in the infrared space for some time. However, the industry has a growing demand for real-time, robust, and highly sensitive measurements that overcome problems like low sensitivity, limited dynamic range, and poor coupling of light into small volumes, as well as dealing with autofluorescence backgrounds. And thanks to modern technology, we now have the QCL advantage to create the next generation of mid-infrared liquid analyzer. So enter the tunable QCL-IR liquid analyzer. And so you ask yourself, well, what are QCLs and what's the advantage of QCLs? Well, Shown here on the spectral intensity plot, you'll note that the y-axis is in log scale, and we demonstrate that the spectral brightness of QCl is many orders of magnitude brighter than an FTIR globar source. And it turns out that this high spectral brightness has significant advantages for the ability to conduct transmission measurements at significantly longer path lengths than ATR methods. And a fixed path length enables quantitative results based upon simple Beer-Lambert principles. No cryogenic cooling is required to cool the detector, and this high brightness equates to data in seconds compared to minutes, hours, or days. So taking a slightly closer look at attenuated total reflectance versus transmission, you can see in this graphical comparison of ATR versus transmission that the ATR sampling depth is limited to about 5 to 8 microns, and as a function of the incident angle theta. Therefore, data is collected through interferometry of the evanescent wave moving along the crystal edge, and comparatively to transmission studies with the QCL, the high spectral brightness punches through large columns of liquid, and therefore allows for transmission studies and also an adjustable path length to optimize your method based upon your needs. And therefore, the high spectral brightness really makes a difference in this case for allowing higher sensitivity and higher quality measurements to be conducted. So, in essence, we're talking about our Colpeo liquid analyzer. So the Colpeo is our second generation liquid analyzer that was purpose-built as a PAT solution for the biopharmaceutical industry. It's based upon pilot work by several Tier 1 biopharma customers, and all of the design feedback has been provided to carry this technology straight into GMP or GXP environments for manufacturing. It features fast, swappable smart flow cell. It ships pre-calibrated with all of the this information needed to track your data experiments. It also boasts OPC UA interface for operating in a QC or manufacturing setting where client system controls may drive the instrument and also control data collection. Has an internal NIST standard calibration check for wavelength accuracy and intensity, and also all the safety features like leak detection, volatile organic sensors, and also laser interlocked defeats when the flow cell is removed. Additionally, this instrument is designed to be stackable and can also operate with our Ceviche autosampler. So it turns out that QCL has a broad range of applications, starting upstream with characterizing media and buffer for quality control. But mainly this instrument is purpose-built as a PAT solution for protein quantitation and characterization, biopolymer syntheses, as well as molecular conjugation or bioconjugation reactions, as well as bioprocess analytics for both upstream and downstream applications. It turns out that there's a number of different modalities for connecting the instrument, either through flow injection or to your autosampler of choice, or even connecting downstream in series to a liquid chromatography system, either a low pressure or a high pressure system is suitable for downstream data collection. The data collection modality is essentially flow analysis, where you're injecting your sample into a flow cell and you're characterizing the wave number versus the absorption versus wave number versus unit time. And so this allows you to scan very fast. In fact, the instrument scans from 1 to 10 hertz at a 2 wave number resolution, which allows you to measure your samples over time and characterize heterogeneities in peak elutions for separations, making it quite nice for peak shaving and also for spotting higher molecular weight aggregates. So connecting the system downstream to, say, like an HPLC system, this is an example of where you can analyze in real time separation from either a high pressure or a low pressure system and collate the UV data to your mid-IR data for secondary structure analysis and so on and so forth. And so the next question is, well, how does this fit into my workflow? And with this, I'm going to turn it over to my colleague Santosh to show some data.
Thank you, Craig. So before we qualify a lead molecule, as it traverses through a pipeline, it undergoes through rigorous characterizations. There are various developability criteria in place for qualifying lead molecules. It begins with sequence analysis, hierarchy structure, carbohydrate profiling, purity characterization, safety, and identity. With QCL, one can determine higher order structures using secondary structure analysis, accurate carbohydrate spectral profiling, protein quantitation, spectral ID for identity testing, lead molecules. So these four analyses can be achieved in a single measurement in real time. So now decision making is a breeze with QCL as it saves time and resources. Hence we say QCL is a purpose-built platform that gives a meaningful insight about your lead molecule. I'm going to share the examples on protein characterizations, carbohydrate analysis, and bioprocess analytics. We can measure protein titer using QCL. So here on the slide, we showed that we collected single-shot scans for lysozyme concentrations ranging from 1 to 135 mg per ml. The data shows great linearity over a wider dynamic range. So you really appreciate here, area under the curve for amide peaks nicely correlates with the protein concentrations. So we are measuring direct amide bond. Therefore, this is a direct measurement that gives you exceptional linearity. In this example, there's an overlay of 4 proteins, lysozyme, BSA, and hemoglobin, and ovalbumin. So first 3 proteins are highly alpha helical in their content, so secondary structure content. Hence, they are showing similar amide profile, whereas ovalbumin, which has 32% alpha helical and 32% beta sheet structure, clearly shows a unique amide 1 and amide 2 profile. Thus, one can use QCL during the clone selection process or formulation studies. In this example, we set up this experiment to track molecular conformation dynamics of glucose. Glucose is a linear molecule when it is solid. Once you dissolve the glucose in water, the solution gets cyclized and its anomeric carbon atom, as shown in this figure. Using QCL, we could track this conformational dynamics of anomerization for a period of 4 hours in aqueous solution. We collected spectra at a resolution of 2 wave number from 1000 to 1200. We could accurately measure the transitions of alpha and beta anomers. So this technology is extremely sensitive for probing a single hydroxyl bond. So one can confidently engage QCL in characterizing glycosylated proteins. QCL can be your great friend in bioreactor monitoring. This is simultaneous multi-component analysis to quantitate both feedstock as well as metabolic waste to support industry's current desire for continuous bioprocess analytics. And this tool can be used online, at line, or offline. It is already being used in a top-tier biopharma in the US for QCing raw materials and bioprocess. Now, let's say if you're in a process of measuring a single analyte in a complex media, well, we already tested that by spiking glutamine into feedstock medium on your left side plot and spiking galactose in a Ham's media. This shows a kind of a pretty nice quantitative correlation. So one can use QCL for single component analysis in a complex matrix. In this slide, we are showing that QCL is highly sensitive in measuring ammonium. Ammonium is used to detect the levels of in a bioprocess media. So this platform kind of gives a single scan mode. We could go up to 25 ppm of ammonia. Now, if you measure in the average scan mode up to 300 seconds, we can easily go down 54 lower up to 0.5 ppm ammonia in the measurements. So this technology can contribute to water quality assessment as well as in bioprocess monitoring for the waste metabolites. Now I would like to hand over to Craig, so he will share our expertise in the QCL-IR space and conclude with the summary. Thank you.
Thank you, Santosh. So for those of you who are not familiar with Daylight Solutions, a little bit about us really quickly. We were founded in 2004, and we're known as the world's leader for tunable mid-IR quantum cascade laser technology, both from instrumentation as well as core or laser components. We have a growing number of publications and Nobel laureates using our instrumentation, and our parent company is Leonardo DRS, an Italian defense firm that purchased this in 2017. So please do check out our website. To summarize for today, mid-IR provides a very valuable chemical information for your bioprocess analytics. It allows you to, it overcomes the challenges of working with aqueous environments. This is primarily due to the high spectral brightness, and we've shown that Copeo is a solid tool for real-time biophysical characterization. It maintains a very high level of data integrity and ease of method transferability downstream. And should you have any questions, feel free to reach out to our team. And with this, I'll turn it back over to the mediator.
Lovely. Thank you so much to Craig and Santosh there.